Kia ora koutou. This is the first video going through some old Pure 3 questions, ones that we can do already. So in this video, I'm doing about 10 marks worth of a paper from November 2025. And there's a question on linearizing graphs, like we did recently in class. It's this one here. And then there's a pretty straightforward complex numbers question. Okay, I think I'm going to start with the complex numbers one, just because it is, I think, a really nice little warm-up one. So let's take a look. We have to find the complex number z which satisfy this equation here. Remember that z star is the Cambridge exam way of writing the conjugate, not like what you'll see in NCEA level 3. And we have to give our answers in the form x plus iy. So we might just start by working out that z times z conjugate is going to be x plus iy. Oops, I really should use the right notation. There we go, x plus iy times x minus iy, which gives me x squared plus y squared. So we can just get into it and substitute in x squared plus y squared plus 5i times x plus iy plus 2 minus 10i is equal to 0. But what we're going to do here is match the real and the imaginary part. So we'll write 0 straight away as 0 plus 0i. So let's clean this up and hope that something nice simplifies. Looking at the real part first, we get x squared plus y squared plus 5xi minus 5y plus 2 minus 10i equals 0 plus 0i. Okay, so that's not just the real part, that's obviously the whole lot all mushed together. But now we can easily split it into the two parts. So the real part gives me x squared plus y squared minus 5y plus 2 is equal to 0. And the imaginary part is very straightforward. It's 5x minus 10 is equal to 0. So we can solve this straight away, and that gives me x equals 2. And now we substitute this in here. We get 4 plus y squared minus 5y plus 2 equals 0. That gives me y squared minus 5y plus 6 equals 0. And a very nice, easily factorizable quadratic. Oops, and that should be a y and not an x. So y equals 2. So x equals 2, y equals 2, or we have x equals 2 and y equals 3. So the two complex numbers we've got that look like they'll satisfy this relationship are 2 plus 3i and 2 plus 2i. Now we can check that pretty easily. So 2 plus 3i times 2 minus 3i plus 5i times 2 plus 3i plus 2 minus 10i gives me 4 plus 9 plus 10i minus 15 plus 2 minus 10i. You can see that the imaginary bit goes, and so does the real part. So that one's good, and we can do a similar check for 2 plus 2i, and they both work. I don't think there's any other solution to that. I'm just having a think about that. Yep, no, that looks good. Okay, let's now move on to the other one, which is the linearization thing. So we're given two variables x and y, but the relationship between them is nonlinear. We're told that ay is equal to b to the power of x. And the first step in this problem is to show that the graph of the natural log of y against x is a straight line. So you're given some pretty detailed guidance on how to start. And from there, we have to use 2 points on that straight line to find the value of A and the value of B. Okay, I'll just make some more. I'll make a new page. Let's just have a look here. Right, well, we start with the relationship we're given, which is AY equals B to the power of X. And we can take logs of both sides. That gives me the natural log of A plus the natural log of y is equal to x times the natural log of b. Now we're asked to show that when we graph, x against the natural log of y, or the natural log of y against x, that we get a straight line. So what we have to do is show that this fits the form where my dependent variable y is equal to some constant times x plus some other constant. We'll rearrange and we get natural log of y is equal to ln of b times x minus the natural log of a. So this is going to be my y, my thing that goes on the vertical axis. This is x. This is going to be the gradient. And this is going to be the plus c. So instead of y equals mx plus c, we've got the log of y is equal to the log of b times x minus the natural log of a. Now, what that means is that for finding the values of a and b, we can use that relationship. I guess if we wanted to, we could plot the 2 points that we're given, and that's a nice thing to do. So let's see what they are. We've got 3.4 and 0.86, and 5.7 and 2.56. You don't have to do this for the question, but I've got time in this video, so let's have a look at what's happening. Right, so this is x, and this is the natural log of y. The 2 points are 5.7 and 2.56, and 3.4 and 0.86. So I'm doing this pretty shockingly badly with no ruler, but let's just go out here. 1, 2, 3. There's 3.4. Let's whack 0.86 about here. So we'll make 1 about here. I haven't drawn it big enough. There we are. So that's my first point. So this one here. And then the second point is going to be at 5.7. 1, 2, 3, 4, 5. About here and all the way up here. So what we're trying to do is we're trying to fit a straight line here. Once you've done a few of these, you definitely won't have to go through this process. But I think when we're starting out, it can help us see what's happening. So we're going to use the 2 values that we've got to fit a gradient like we did back in year 9 or 10, and then to find the constant. We just have to be a bit careful with what it is. So m here is not the change in y, but the change in log y divided by the change in x between the 2 points. It doesn't matter which way around we go. Also, just be really careful that we haven't got y here. This value here is the natural log of y already, so we don't need to log it again. So the change in the natural log of y is 2.56 minus 0.86, and the change in the x values is coming from here, so it's going to be 5.7 minus 3.4. So we get 1.7 over 2.3, and that gives me m of roughly 0.73913. And if you're looking at our graph, like that looks about right. Now then we go back to the relationship we found up here, and we know that that m is the natural log of b. So we can say the natural log of b is equal to 0.73913. We exponentiate it. I think that's the right way to say it. We e both sides, right? So b is equal to e to the 0.73913. B is equal to 2.094. And I think we were asked to give that to 2 significant figures. So b is roughly 2.1 to 2 sig fig. Next, all we have to do to find a is we're going to substitute a point in, because we can see that now what we need to get is the constant. So we've got the natural log of y is equal to the natural log of b times x minus ln of a. We can pick either point, but I did 3.4 and 0.86. That gives me 0.86 is equal to 0.73913 times 3.4 minus the natural log of a. Ln of a works out to be 1.653042, and that gives me, when I e both sides, A is equal to 5.2228. So again, rounding that to two significant figures, we get A is equal to 5.2. Now, I don't think we were asked to put it all back together, but let's just see what it looks like. Whoops, that's tomorrow's question. We're not doing that yet. Okay, so we're told that we've got this relationship here. Putting it back together, we've got 5.2y is equal to 2.1 to the power of x, which looks kind of weird. So we could write it as y is equal to, oh, this looks even weirder, this. So there you go, that's the curve that we are really working with here, but we've used a really useful technique of logging both sides and then plotting a linear relationship to figure out the parameters of the model. Great, thanks for watching. I'm going to try and do one of these a day, so if you've got any special topic areas that you want covered, let me know. Otherwise, I'm just going to go through some old papers and pick out bits that we can do already.